Hi, thank you all for joining today, and thank you to the organizers for the invitation. I'm Niranjani Prasad, and I'll be talking today about my work on developing methods for the application of reinforcement learning to clinical decision support in acute patient care. So the planning of the management of routine interventions makes up a significant part of patient care in the ICU. These interventions can include, for example, sedation and pain management, the transfusion of blood or other fluids, or various modes of mechanical ventilation. Delivering these interventions in a timely, measured way can greatly improve patient outcomes and reduce hospital costs. But in many cases, they are not particularly well understood and their effects are poorly quantified, especially for heterogeneous patient populations. This means that in practice, these decisions are made in an ad hoc way, driven by factors that are sometimes independent of clinical imperatives. And so we therefore end up seeing significant differences in protocol, both across hospitals and in the behavior of individual caregivers within a single center. Taking first the example of invasive mechanical ventilation, this essentially refers to the use of mechanical means to assist or replace spontaneous breathing. It is one of the most common interventions in the ICU, necessitated by a broad range of underlying conditions. Ventilator support is also typically coupled with sedation, which needs to be carefully regulated to maintain the comfort and physiological stability of the patient. It's estimated that about 40% of ICU patients are ventilated at any given hour, and that this accounts for about 12% of total hospital costs in the US. When we talk about weaning, we refer to the process of taking a patient off ventilation. This is a series of steps that involves gradually reducing sedation levels, changing ventilator settings, and carrying out breathing trials. And this entire process can take up to 40% of a patient's total time on the vent. Both premature and delayed weaning are associated with worse outcomes for the patient. Prolonged ventilation and corresponding oversedation is associated with high rates of post-extubation delirium, drug dependence, ventilator-associated pneumonia, not to mention inflating costs and straining hospital resources. However, what we see in many hospitals in the US, at least under normal circumstances, is that physicians tend to be conservative in recognizing patient suitability for extubation, as failed breathing trials can cause severe discomfort, and early extubation that leads to the patient being placed back on the vent can result in even longer ICU stays. What we aim to do in this work is to develop a clinician-in-loop decision support tool that can alert caregivers if a patient is ready for weaning and recommend sedation and ventilation settings accordingly. And we aim to do this by modeling the system as a Markov decision process, or MDP. In this setting, our agent is the clinician and the environment is the patient's state at a given time, as observed through the electronic health records. At each time t, the clinician observes state st, takes some action at accordingly, and receives some feedback r that reflects the suitability of the action at this time step. We've chosen to tackle this problem in the reinforcement learning framework as it is fundamentally a sequential decision-making problem rather than purely a prediction task. So given examples of behavior in which agents might be acting suboptimally, we wish to choose the best possible action at each time in terms of drug dosage or vent settings, while capturing the stochasticity of the underlying process, the delayed effects of actions, and the uncertainty in state transitions and outcomes. This poses a number of challenges. There is a large space of possible predictors, not all of which may be directly observable from the patient's EHR, as well as a complex set of interventions available to clinicians in practice. The data we do have is often sparse and noisy, and subject to censoring of outcomes by the actions that are actually taken in patient histories. This can make it harder both to learn and to evaluate policies. In the first part of this talk, I'll discuss our methods for extracting and processing critical care data for this problem to address some of the challenges described, how we then represent these patient histories as an MDP, and solve for an optimal policy using batch reinforcement learning methods. And lastly, how we can begin to evaluate these policies using the data we have available. The second half of my talk will probe further into the challenges in reward design for reinforcement learning and clinical decision-making tasks. I'll describe my work on methods to solve for optimal policies in multi-objective RL through the lens of decision support for lab test ordering, as well as work on constrained reward design to guide safer policy learning. Finally, I'll outline ongoing efforts to apply the methods described to guide electrolyte repletion in the University of Pennsylvania health system. and discuss a little bit the work needed to pave the way for sustained clinical adoption of these decision support tools. So returning now to ventilation weaning. As I've mentioned, what we're trying to do is learn an optimal policy from examples in historical data. The dataset we're working with here is the MIMIC3 Critical Care Database, a publicly available de-identified dataset of ICU admissions from a Boston hospital between 2001 and 2012. It includes data for about 53,000 adult admissions, as well as about 8,000 neonates. Of these, we filter for adults who have been successfully discharged from the ICU. We do this as those patients who don't survive the ICU tend to have been more severely ill, and ventilation weaning protocol is unlikely to have had significant impact on patient outcome. We also filter for only patients who spend an extended period of time on ventilator support, which we define as more than 24 hours. This allows us to exclude short episodes of routine ventilation, post-surgery, for example, where again, weaning protocol is less relevant to patient outcome. For the 2,000 or so patients that we selected in this way, we extract data on vitals, lab tests, medications, etc. Illustrated here is a typical patient admission in the dataset. The patient here is in the ICU for about 4 days and on ventilator support as well as intravenous sedation for the majority of this time. Shown also are time-stamped nurse-verified vitals recordings for oxygen levels, arterial pH, etc. We can see that these different vitals are measured at very different frequencies. This is typical of EHR data. Measurements tend to be sparse, irregularly sampled, and error-prone. One way to tackle this would be to filter out extreme values in measurements, resampling, and imputing missing values by simply carrying forward the last known measurement. This can be a reasonable thing to do, as values aren't usually missing at random. Samples are taken when a change is suspected. However, this naive method does limit the possibility of more fine-grained recommendations, so it's worth us considering more sophisticated imputation methods. Specifically, what we use here are Gaussian processes, which have been widely applied to clinical time series. A Gaussian process can be thought of as a distribution over functions, where each point in the continuous input space, in this case time, is associated with a normally distributed random variable. Here, we use multi-output Gaussian processes to jointly model time series of vitals by estimating the covariance structures between them. Shown here is the mean and confidence intervals from our imputation for 2 vitals, heart rate and arterial pH, for one example admission. Now that we have this, we can query the predictive mean of the Gaussian process at hourly intervals to obtain a regularly sampled time series for each patient admission. For our training data, we use all available measurements for each patient when imputing. In the test set, we use only those patients prior to the time point to be queried, which is the only information we would have available to make a decision. Now that we have our cleaned up patient histories, we need to formulate them as Markov decision processes. What we want to learn is some policy pi mapping from states to actions that maximizes return, that is, the discounted cumulative reward over the patient admission, where discount factor gamma determines the relative importance of immediate and long-term rewards. In designing our state variable S, we want features that are rich enough to provide good predictions about action values, but that are simple enough to allow us to learn from a limited amount of data. What we use here is a 32-dimensional feature vector comprising static demographic information, such as age, weight, admission type, as well as time-varying vitals, administered sedatives, as well as relevant high-level information, such as vent duration and number of reintubations so far. Our action space for this problem is a simple, discrete space of 8 possible combinations of vent settings and sedation dosages. So the first element can take values 0 or 1 for whether the patient is kept on or off the ventilator, and the second takes one of 4 possible dosage levels. This is created with the help of domain experts to map the various administered sedatives all into a single scale. Our transition function for this MDP defines the system dynamics, and in this case, as in most real-world examples, is unknown. Finally, feedback comes in the form of the reward function, which may depend on the state, action, and observed post-state. At the center of reinforcement learning is the assumption that the reward represents the most succinct, robust, transferable definition of our task. But often, there are many reasonable feedback functions we could define, since patient health can be described in a number of ways. And an ill-defined reward can cause the RL agent to learn various modes of unintended behavior. Here, as a starting point, we draw from weaning guidelines established by the Hospital of the University of Pennsylvania, comprising a checklist on physiological stability and oxygenation criteria. Taken together with what we know from clinicians about undesirable wean outcomes, we design a reward function that penalizes abnormal or highly fluctuating vitals, prolonged ventilation, failed spontaneous breathing trials, or reintubation within the space of an ICU admission. So now that we have our sequences of states, actions, and observed rewards, we want to use these transitions to learn an optimal policy. And we do this by first estimating the value Q of the state action pairs. That is, the expected total discounted reward when starting from a given state action pair. In naive Q learning, we start from some arbitrary estimate of Q and update at each new state transition using the Bellman recursive equation. Our new estimate of Q is then a convex sum of our old estimate and of the immediate reward plus the maximum Q value estimate of the next state. Here, the learning rate alpha gives the relative weight of the current and previous Q estimates. In our setting, we want to learn an approximation of the Q function over a continuous state action space using a finite set of transitions that have already been collected. For this batch setting, we use fitted Q iteration, or FQI, which reformulates the Q function determination problem as a sequence of K supervised learning problems. The training set of the kth problem is defined as follows. The input is all state action pairs, and the target is given by the Bellman update rule, the immediate reward R, plus the discounted maximum expected value from the next state. At the first iteration, this produces an approximation of a Q function corresponding to a one-step optimization, that is, an estimate of the instantaneous reward given the state action pair. It follows that running this over K iterations gives us the expected value of a over a K-step optimization horizon. So each iteration of FQI uses a complete set of transitions to update its estimate of Q. This makes it unique from Q learning, which uses a single transition to update Q at each step, or methods based on deep Q networks, which usually use a mini batch of recent experience. This efficient use of available experience has made FQI popular in healthcare and other settings with limited data. The algorithm is also flexible in that it can be used in conjunction with any function approximator and has convergence guarantees for several common regressors. Here, we consider FQI both with tree-based methods and with simple feed-forward neural networks for modeling Q. Once we've converged to our estimate of the Q function, the optimal policy is given by the action that maximizes the estimated Q value of each state. Shown here is what our optimal policy on ventilation need looks like for an example admission. The patient is in the ICU for about 100 hours and taken off the vent just before discharge, as shown by the orange line. For comparison, we train a logistic regression model directly mapping states to actions in the dataset, so this acts as our baseline. We can see that this roughly matches the clinician policy exactly for this admission, taking the threshold of the probability of ventilator need as 0.5. Our policies learned from FQI, on the other hand, recommend that the patient is taken off the vent at around 40 to 60 hours into the admission. What this suggests is that an alert at this time could save up to 2 days of unnecessary ventilation. This does give us an intuition for why we do not want to evaluate our methods simply according to how well they reproduce clinical behavior. Instead, we need to consider the reward function that the policies are optimizing for. To do this, we split our test admissions into 6 approximately equal sets, delta 0 to delta 5, according to the extent to which our policies for these admissions match the clinician policy. So delta 0 are admissions that match almost exactly, while delta 5 are those that deviate most. Plotting, for example, the distribution of the number of intubations in an admission, we find that patients in delta 0 undergo no reintubation, and in general, these rates of reintubation in admissions increases with the deviation from the FQI policy, with patients in delta 5 undergoing up to 7 reintubations. Similarly, plotting the overall mean accumulated reward over patient admissions in each set, we can see that those admissions in set delta 0 tend to have a high mean reward, while those in delta 5 have lower mean rewards, and also see a much wider distribution in returns across the set. While there are certainly sources of confounding here, what I hope to convey is that this provides some evidence that the policies learned are able to identify clinician behavior in admissions that is associated with positive patient outcomes. So in summary, I propose in this work a data-driven approach to the optimization of weaning from mechanical ventilation of patients in the ICU. Patient admissions are modeled as Markov decision processes with novel representations of state, action, and reward developed in this framework. Reinforcement learning with fitted Q iteration using different regressors is then used to learn a simple ventilation weaning policy from examples in historical ICU data. And we demonstrate that the algorithm is capable of extracting meaningful indicators for patient wean readiness and shows promise in recommending sedation and extubation time that can improve on current clinical practice. However, we also find in our experiments that policies are sensitive to the relative importance of different objectives in the definition of the reward function, which at present we set somewhat arbitrarily. Additionally, our evaluation of these policies here is rather coarse, although it presents a pathway for preliminary qualitative analysis of the learned clinical policies. That serves as a starting point for much of our ongoing work. In part 2 of this talk, I introduce two possible frameworks for tackling these issues from the perspective of reward design. In developing the first of these approaches, I consider the problem of ordering lab tests for patients in intensive care. The precise targeted monitoring of patients is central to care in the ICU, and lab tests requiring invasive procedures are estimated to influence up to 70% of diagnoses or treatment decisions. But increasingly, there has been several concerns about the over-ordering of labs in the ICU. For example, because of multiple clinicians treating the same patient or recurring orders being placed too often for clinically relevant changes to be detected. What we aim to do here is to use our MDP framework to obtain policies for lab test ordering, again using patient records from MIMIC resampled at hourly intervals. We choose to learn ordering policies for 4 common labs: white blood cell count, lactate, blood urea nitrogen, and creatinine. Each of these is crucial in the diagnosis of conditions associated with high mortality in hospitals, such as sepsis or acute kidney injury. Our state variable in this case is a 13-dimensional feature vector comprising the SOFA score, which is a metric of severity of illness that encompasses several other variables, as well as heart rate, respiratory rate, etc. The 4 labs, and corresponding delta terms with the elapsed time since each of these labs was last taken. Our action variable is simply a binary variable indicating whether or not a lab is taken at time t. And finally, rather than a scalar valued reward that decides a priori what the trade-off should be between different clinical objectives, here we have a 4-dimensional vector function in which each element reflects feedback with respect to a different clinical objective. Namely, we want a policy that recognizes physiological changes promptly, maximizes the amount of actionable information in lab tests that can directly inform treatments, minimizes the information redundancy in ordered tests, and minimizes the effective cost to the patient of each lab test, both economic and in terms of comfort. We now need to solve this multi-objective MDP for an optimal policy. And to do this, we adapt methods from multi-objective fitted Q iteration that draw from ideas in Pareto optimization. So a vector-valued RT, a reward, means a vector-valued function of state action values Q, or in other words, a Q function corresponding to each element of the reward function. Learning the value of state action pairs with respect to each objective in this way allows for more interpretability in weighting the relative importance of each objective. But given this 4-dimensional Q, how then do we choose a single optimal action at each time when updating our estimates of Q? So our approach here starts by generating a Pareto partial ordering. So then at each time step, we eliminate any actions that are strictly dominated by another action in all dimensions of the reward. Secondly, in this specific task, we decide that our priority is to strictly limit unnecessary labs. So we take this one step further and eliminate action 1, that is to take a lab, if it is dominated by action 0 in any other dimension. This domain-motivated pruning of the space of optimal action sequences allows us to scale to longer episode horizons and still produce a deterministic policy. We evaluate our recommendations using an importance sampling based off policy estimator. This illustration here gives some intuition for what this looks like when evaluating deterministic policies. We start with a large cohort of patients in different states and observe different lab test ordering decisions at each time step. Consider that the policy we wish to evaluate follows the path highlighted in blue. Our estimate for the value of this policy is then the discounted cumulative reward observed by the patients in the data that follow this path. By the patients in the data that follow this path. Here, we use a variant of this called per decision weighted importance sampling, which uses the cumulative reward after each time step to get the final value of a policy, yielding an estimate with lower variance. This is used to compare our learned policy with the current behavior policy, which we estimate from the patient histories, as well as several random policies with different test recommendation frequencies to use as baselines. We find that our policy in blue consistently outperforms the behavior policy in red and tends to outperform the others in most objectives across our policies for all 4 labs. Learned policies also show a 27 to 44% reduction in the total lab orders and an improvement in the average usefulness of recommended lab tests over clinical behavior, by which we mean increasing both the mean information gain, that is the deviation of the actual measurement when taken from the forecasted value, and the time between the recommendation and the onset of a key treatment or intervention, potentially allowing treatments to be initiated sooner. Overall, this multi-objective approach shifts the setting of priorities from being embedded in the MDP towards the designer or the user of the RL agent, allowing for more flexible and interpretable recommendations. In more recent work, I explore how we can take this one step further to guide the agent designer in choosing a reward function from a restricted candidate set of convex combinations of reward components, and doing so in a way that the reward reflects what we implicitly know from the data about reasonable behavior for a task and facilitates robust off-policy evaluation. We can rephrase this question as follows. For what reward functions can we learn policies that are consistent in that they do not diverge too far from observed behavior, and evaluable with high confidence performance guarantees, given that we only have a set of past trajectories collected from flawed but safe expert behavior? This is common in many real-world scenarios, from healthcare to education or finance, where the risks of deploying an agent are high, but logging current practice is relatively easy. Here, we draw from literature on inverse reinforcement learning to assume that the reward R can be written as a linear combination W times phi, where phi is a vector function of state features. We can then write that an optimal policy pi, maximizing this expected cumulative reward, can be written as the expectation of the discounted sum of W phi. And finally, factorizing out weights W from this expression, we can write the expected value as W mu. Mu denotes the feature expectations of the policy, or the expected discounted time that the agent spends in each feature state. We can think of this as a representation of the dynamics of a policy that is decoupled from rewards. Our first set of constraints on ensuring policy consistency are founded on the assumption that the behavior seen in batch data may be biased or inconsistent, but generally achieves reasonable performance with respect to the true objectives of the task. We therefore want a policy optimized with our reward function to be epsilon close to the available data, in terms of the feature expectations mu, and in turn the expected value W mu. We formalize this here for our definition of the consistency polytope PC, which constrains the value of our policy to be within a factor epsilon above or below the value of the behavior in the available historical data for reward weights W. Consider, for example, a toy environment in which the agent starts at the origin and must reach one of 2 goal states in the top left or top right of the environment. If we have batch data where the large majority of trajectories follow a path to the second goal state, a reward function consistent with this dataset would encourage similar behavior, for example, by placing positive weights on both the x and y coordinates. Next, we want to ensure that our confidence in our evaluation of a learned policy before deploying it in high-risk settings. One possible metric for safety is the ability to calculate a high confidence lower bound on the performance of the policy. Here, we obtain this lower bound by adapting existing concentration inequalities to bound our off-policy estimate of mu. Our polytope of evaluable reward weights, PE, is then defined as those for which the lower bound on performance is within some threshold tightness of the expected performance mu. For some intuition on why these 2 constraints are not equivalent, consider that the extent of overlap must depend, for example, on the homogeneity of behavior in the batch data. Consistency is essentially measured with respect to the average behavior in the data. if there's a considerable amount of exploratory behavior seen in the data, or if the data has been collected from multiple agents with different behaviors, for example, from different care providers, then the space of policies that can be evaluated given the batch data may be larger than this policy space consistent with the average expert within some epsilon. Having defined our two sets, our polytope of admissible reward weights W finally just lies at the intersection of weights that satisfies both the consistency and evaluability criteria. Note that these sets cannot be explicitly described. There are an infinite number of policies with corresponding representations mu, and so infinite possible constraints we could draw between admissible and inadmissible weights. Instead, we construct a separation oracle to test in polynomial time whether a point lies in the admissible set. So given our admissible set P within the space of all possible reward weights, we first test the weight vector of interest W initial against each of the imposed linear constraints. If these are satisfied, then W initial lies in the polytope of interest. If not, then the oracle uses the failed constraint to output a separating hyperplane such that P lies inside this half space and W initial lies outside it. Now that we have this separation oracle to test whether a given reward, for querying whether a given W lies in the admissible reward polytope, we have what we need to optimize linear functions over this set. Specifically, given some initial reward proposed by the user, we can solve for the closest admissible reward using either exact methods or using more computationally efficient iterative search techniques based on the follow the perturbed leader algorithms. Let's now see what these polytopes might look like for a real task. Returning to the ventilator weaning problem, we formulated our original reward function to take the form of a linear combination W of three interpretable reward components: a penalty on prolonged vent duration, a penalty of abnormal vitals, and finally, a reintubation penalty. To visualize the distribution of admissible weights when training policies on the extracted patient histories from MIMIC, we sweep over weights across the 3D space and evaluate each against a separation oracle for the corresponding policies. Admitted weights for some choice of threshold on consistency and evaluability are highlighted here in green. We see here that these are clustered at large weights on the vitals penalty term, that is, on physiological instability while off the ventilator. This basically has the effect of favoring policies that are conservative in weaning patients, and suggests that admitted weights seem to reflect the biases or preferences in the behavior seen in the batch data. To understand how this might play out when using our iterative search method to guide reward design, consider a scenario in which the designer of this decision support tool is primarily interested in minimizing vent duration, and so chooses a naive initial reward that penalizes only duration, so W is 100. Following 10 iterations of our iterative search algorithm, this shifts to final weights that look more like this, which so essentially distributing non-zero penalties onto reintubation risk and physiological instability, yielding a policy that's closer to the conservative behavior observed in the batch data. So to conclude this section, what we're presenting here is a method for guiding reward design for RL using batch data from suboptimal experts. We formulate constraints on rewards to those for policies close to experts and with acceptable bounds on performance, and demonstrate how rewards can be chosen in practice from the space of functions satisfying these constraints. What we'd also want to take away from this is that reinforcement learning in safety-critical settings is necessarily an iterative process of deployment and evaluation to move our policies incrementally towards ideal behavior. Finally, in this last section, I'll be briefly describing some of my ongoing work in collaboration with the Hospital of the University of Pennsylvania, applying these methods to another common critical care intervention, namely electrolyte repletion. So electrolytes are charged minerals such as potassium, magnesium, or phosphate that are essential to maintaining normal cell function, as well as playing a key role in electrical conduction within the heart, muscle, and nervous systems. It follows that electrolyte imbalances are associated with higher morbidity and mortality rates in patients, so repletion of electrolyte levels is a significant task in critically ill patients. While hospitals typically have certain standardized protocols in place as guidance, adherence to these are poor, and repletion decisions are largely driven by individual clinicians. And there is considerable evidence that biases from this provider-directed approach lead to significant errors. doctors are prone to more missed episodes of low levels of electrolytes, and increasingly, there's a high rate of unnecessary repletion events. In this work, we consider a large data set of admissions over a 5-year period across 3 different hospitals in the University of Pennsylvania health system, and extract admissions with repletion events for key electrolytes. Focusing here on potassium, shown here is a distribution of measured potassium levels immediately before and after a repletion event, along with a target or reference range of potassium values in blue. We find, surprisingly, that more than 4% of all supplements are administered when potassium is above the reference range, increasing the risks to the patient of hyperkalemia. At the same time, many repletion events at low potassium levels appear to be ineffective, as they fail to bring measurements into the reference range. This motivates the use of a more data-driven approach to decisions on when and how to administer potassium. As before, we considered this decision-making problem as an MDP, formulating a 52-dimensional state space with both static and time-varying features of patient physiology, as well as any procedures and medications that may have direct or indirect impacts on potassium levels, such as the administration of dialysis or non-potassium-sparing diuretics. Our overall repletion policy is made up of 3 optimized sub-policies, mapping from this state space to one of 3 distinct action spaces. First, we learn a policy to decide the route of repletion, whether by oral tablets or intravenous therapy, both or neither. For each of oral or IV repletion, we then learn a policy to determine the most suitable dosage level and infusion rate in the case of IV. Dividing the problem up in this way helps facilitate our policy optimization task and essentially mimics the hierarchical decision-making process that is likely implicitly used by clinicians in practice. Finally, we take the reward function to be a weighted linear combination of 4 elements, corresponding to the cost of oral repletion, intravenous repletion, abnormally high potassium, and abnormally low potassium, respectively. In order to better understand current clinical practice and in turn determine how to set our priorities and clinical objectives for our optimal policy, we first apply an inverse reinforcement learning or IRL-based approach to inference of the weights in the reward function R, where R is equal to W phi, as optimized by clinicians in the historical UPHS data. The fundamental strategy of most algorithms for inverse reinforcement learning is as follows. So we first initialize a reward function parameterized by some weights W and solve the MDP given this reward function for an optimal policy. We then estimate some representation of the dynamics of the RL agent when following this optimal policy, such as just the state visitation frequency, or as in this case, the policy feature expectations mu, which we defined previously as the discounted time spent in each state. Finally, we compare this estimate with the dynamics observed in the available batch data and update W to shift learned policies towards this behavior. And we iterate until the learned optimal policy is sufficiently close to behavior. When we run this on our data set of potassium repletions in the UPHS data, we find that we obtain small negative weights on both the cost of IV and the cost of oral repletion. That is, clinicians associate the administration of potassium supplements with positive rewards. Also, the penalty associated with low potassium levels is significantly higher than that for high values. This provides some evidence in support of concerns that care providers either tend to order potassium supplements reflexively without fully considering cost or clinical necessity, and may be unnecessarily conservative in avoiding potassium deficiency. We try to correct for this to an extent when learning our optimal policy by shifting instead to small positive weights on repletion costs while keeping other weights approximately the same. So learning Q estimates using FQI with this final reward function, we construct the hierarchical treatment strategy we described earlier for recommending repletion route and dosage. Recommendations for an example hospital visit are shown here, along with actual repletion events in the UPHS data. We can see that the FQI policy shows a preference for oral repletions, which are associated with lower risks and costs. Unlike the historical data, all recommendations occur when potassium is below the reference range, and IV repletions are only recommended when the patient is significantly hypokalemic. To investigate the factors influencing our final treatment recommendations, we train a pair of classifiers mapping from patient state to recommended oral or intravenous potassium. Shown here are the Shapley values for the classifier for oral potassium supplements. So what this tells us is the contribution of each feature of a sample patient state in pushing the probability of repletion up or down, away from the population mean prediction. So a high Shapley value for a sample feature means a higher probability of recommended repletion. The colors here denote the corresponding feature value for each sample. So as expected, current potassium levels is the most influential feature, with low potassium levels associated with higher probability of repletion. We also find that oral repletion is more likely to be recommended at high levels of sodium, which tends to be inversely correlated with potassium, as well as at high urine input, causing high potassium loss, likely because the patient was administered some non-potassium sparing diuretic. Finally, we can produce a quantitative estimate of the value of our learned policies offline using the more recently introduced fitted Q evaluation method, which adapts the iterative Q function estimation method in FQI to the task of policy evaluation. The violin plot here gives the distribution of estimated Q for all state action pairs in the potassium repletion cohort. So remember that these values are essentially weighted estimates of the total discounted repletion cost and penalties for electrolyte imbalance. We can see here that the mean value of the FQI policy is significantly higher than that of the estimated clinician behavior. So this approach therefore has the potential to ease the burden of unnecessary prescriptions for the pharmacist, reduce demands on the clinician, and lower costs for the hospital without compromising on patient outcome. So just to finish, what we look to do in this work is to try and bridge the gap between the decision-making process in hospital settings and planning as a machine learning problem. We describe a generalizable framework for modeling EHRs of inpatient admissions as Markov decision processes, and we demonstrate this over multiple critical care tasks and data sets. We adapt data-efficient batch reinforcement learning algorithms to learn optimal policies for these MDPs, and we've introduced certain mechanisms for guided reward design, working towards safe batch reinforcement learning in this high-risk setting. So there are a number of possible next steps for extending the modeling framework introduced here. Some of the directions I'm most excited about, for example, include learning better state representations for the patient's underlying health, either using latent variable models or modeling the patient as a POMDP that maintains a distribution of the belief state. Formalizing the initial ideas here on hierarchical clinical decision-making using tools that exist in RL, such as the options framework. Developing methods for choosing discount factors appropriately and tailoring these perhaps to different sub-objectives that act over different horizons by applying domain knowledge, as well as on a larger scale, extending these ideas to resource allocation or multi-agent reinforcement learning tasks, where our environment is instead, for example, an entire ward with resource constraints rather than a single patient. Finally, the work we've described here is simply the first of a series of challenges to the sustained adoption of these tools in practice. So a necessary next step, of course, is to clearly quantify the estimated value addition of the tool in terms of clinical outcome, as well as cost and time saved, in order to justify the launch of prospective studies and show how this value generalizes across different hospitals, across different demographics, and over time. And this, of course, requires to an extent development of current off-policy evaluation methods. Having done this, a thoughtful approach is needed for the reporting of recommendations in a way that is sufficiently transparent and flexible given the constraints faced by clinicians. Finally, methods are needed to continually monitor these systems, consider how the policies we introduce may affect pressures at different stages of the healthcare pipeline, as well as counter temporal drift or reinforcement of any biases that may be present in the data. Recent events have drawn sharp focus to how precarious our current health infrastructure is, as well as the pressures faced by healthcare workers. This is true on a global scale. Carefully implementing these sorts of data-driven tools is one way in which we can help ease these pressures, streamline care, and try to ensure we're better prepared to tackle future crises. So I'll finish there. Thank you all for listening, and thank you all also to all my collaborators who made this work possible: Barbara, Lifang, Corey, Michael, and Finale. Thank you again.